And it ended up being like
Okay, we should get started. Okay. All right, let's quiet down, guys. Let's get started. It's 3:10. Okay. All right, so so today's Friday. We have our help session tonight at when? 5, 6, 5. So it runs from 5 to 7, I guess, officially. All right, over in ARC. Okay, you just look for people. Okay, find us. I'll be there around 6. All right. So we have class one day next week, don't we? Monday? Wednesday.
No, just Monday.
No, Monday. Okay. Sorry, I misheard. Okay. That's good, I guess. So we can do one more lecture then. So, I still don't know exactly what we'll do the final week, but so I think there was something that I wanted to do today, but I'm going to push it back to Monday so that it's after everyone has done PA6, because it sort of would contain some spoilers, I guess, for PA6. So I guess the idea is that what I want to do is talk about some theory today about sort of how to implement a type inference algorithm, or how to kind of write a different kind of type checker, and then we can put it into practice a little bit next time to see kind of what happens if we take PA6 and rewrite it in this way. So I think that'd be cool, or maybe not the full language of PA6, maybe a subset of it, just to keep it easy. Right. So let's remind ourselves a little bit of what we did last time. Suppose I could pull up the notes. What did we have? Right, so I introduced the idea of type inference or type reconstruction. And the idea is that, well, let's take our types, whatever they were before. Maybe we had Boolean and then arrow types and whatever it is, and let's add type variables. So now a type can also be a type variable, where it's just a string. Okay? And so now, given a term, it could contain some type variables now in places where types would normally appear. And here's some example types. I mean, just x by itself could be a type, but you could also have something that looks like x arrow x, or you could have x arrow y, or bool arrow x, or it could be anything where now type variables are a part of the syntax of types. And so now, given a term t, that you could say either when the type annotation is omitted, or maybe just where it has type variables. Now, you want to find a way to give concrete types, to kind of get rid of all the type variables, such that the term will be well typed. Okay. Right. So you want to find a substitution. So there are a couple new ideas here. I mean, so once you have variables in types, now there's this idea of like, what are the variables of a type? Or we could call it free variables, which I could write like FVs. So say you've got some type t, then the free variables of the t will be like a set of string or something. It's like, what are all the variables that appear in the type? Okay, so what are the free variables of this type? Just the set containing x. Same thing here. But if you had another type like x arrow y arrow z, then the free variables would be x, y, and z. And we looked at something similar for terms before, for expressions. Like, what's the free variable what are the free variables of an expression. And there it was a little bit tricky because our expressions could bind variables. They could have sort of their own local variables. So you'd have to be sure that, not to include those. They're not considered free if they're bound. So it was a little bit complicated for expressions. But in types, it's very straightforward. It's essentially, if the variable appears anywhere in the type, then it's in the free variables of the type. So it's very easy to compute free variables of a type. All right. Yeah. And then to sidestep a little bit, or to a slight detour before we get to more type inference stuff, is that we were just talking about parametric polymorphism, how it differs from these other kinds of polymorphism. And there are a couple ideas here, like so polymorphic types are types that look like this. You call them universal types. Okay, they're types with for all quantifiers like that. And so we had a couple words here that we used. We say a monotype is a type that doesn't have any quantifiers. Okay, so here's some example monotypes. And so then, of course, there are polytypes, polymorphic types, whatever, that are types that do contain quantifiers. Okay, but then there's some stuff here about kind of where the quantifiers appear. Okay, so we said, well, there's a special kind of a special case of polytypes where all the quantifiers are all the way to the left. So that's called prenex. Okay, and then there was something very similar to prenex. So here's prenex, all quantifiers are to the left. But there's a related idea called rank 1, which is where all the quantifiers are not to the left of an arrow. Okay, so obviously prenex implies rank 1, because if the quantifiers are all over here, then they're sort of at the they're not under an arrow to the left. They're just on the outside. But rank 1 polymorphism is a little bit more permissive. It says, well, the quantifiers don't have to be all the way to the left, but they just can't be to the left of an arrow. So if you take the type and draw it as a tree, so we took an example here where I think we were drawing this type here at the top, okay, where it says for all x, x arrow, for all y, y arrow x. So that quantifier is not all the way to the left, but when you draw this type as a tree, it looks like this. And it's still okay. Well, it's rank 1, okay? Because this quantifier here is to the right of an arrow, not to the left. And there's never any quantifier to the left of an arrow. And so any rank 1 type like this, you can take these quantifiers and move them up and to make them prenex without changing the type. You'll have an equivalent type. So that's why we use these terms kind of interchangeably. Prenex polymorphism and rank 1 polymorphism. That means types that where all the quantifiers are all the way to the left, or that where they could be moved to the left without changing the type. Okay. And then there is this generalization where you can say, well, rank n is when they're not to the left of n or more arrows. So you can be a little bit permissive. You can say, well, rank 2 polymorphism will allow the quantifiers to be under 1 arrow, but not more than 1. Okay? And the reason that we care about this does kind of circle around to this idea of type inference. Because, well, for rank 1 and rank 2 polymorphic types, if all of the types are restricted to being rank 1 or rank 2, then you can always do type inference. That it's a decidable problem in that kind of restricted case. But for rank n, where n is greater than or equal to 3, then the type inference problem is undecidable. So you can't always infer the right types whenever they can be, overly complicated. Okay, so that's our little review of last time. And so what we're going to do now is kind of focus in on this special case of rank 1 polymorphism or prenex. all right, because we like it when type inference is decidable. So that's what I want to do. I'm going to start introducing some ideas for how to go about doing this. Okay, so we can kind of explore how to implement this kind of polymorphism in a language with type inference. Okay, so that the programmer doesn't have to specify any types at all, and the type checker can infer the types. And you know, the thing is, it can infer even polymorphic types. Okay, so for example, let's add a new thing. So if you give it a function that's like, you know, I'm going to use lambda notation. So you say lambda x dot x. Okay, this is the identity function, but we haven't given it a type for x. Okay, so this doesn't have to be the identity function on numbers or on booleans, but it can be polymorphic, right? The type of this could be, or it should be, for all big X, X arrow X, right? So this is the type. And so we would want our type system to be able to infer that type. So, and you know, it could choose to give it the type num arrow num, right, or bool arrow bool, and those would actually be perfectly fine. This would be a well-typed term with those types. But there's this idea of the most general type possible. This is the most general type. You call it the principal type. And so we're going to have a type inference algorithm that not only will it find something that works, it actually finds principal types always. So it finds the most general types. And that's a really desirable property. Okay? But it'll take us a little bit to get there. So that's what we'll do now. All right? So we've already looked at type variables. That's kind of what these things are for. This big X. Okay? And then, so once you have variables, then, well, you know, what did we have to do to support variables before? Well, we had like an environment that would map variables to things. Okay, or you can do substitution. Okay, so we're just going to stick with substitution. We're not going to use any kind of environment. We're going to say, well, now that we have variables, we're also going to have a notion of doing substitution in types to like substitute types in for the variables. So I'll write it like this. So I'll say a type substitution, which I'll usually denote with sigma, little sigma, is just a mapping from variable names, from variables to types. Okay, and okay, so then given some type substitution sigma and a type t, then we'll write it like this: sigma t is the result of applying the substitution to the type, right? So result of applying sigma to t. Okay, so if sigma is a mapping, like what would be an example of a type substitution? So we'll write it like, it could say, well, map x to num and y to bool. Okay, suppose that's our sigma. I'm not very good at drawing sigma. And then suppose that t is the type x arrow y. Okay, well, so then sigma applied to t will be num arrow bool, right? But these can be kind of complicated. So notice what I said, sigma is a mapping from variables to types, but the type variables we have are themselves types. They're a part of the language of types. And so a type could also be a variable. So you could also have something like, sigma equals x maps to y, right? And And so then sigma applied to t here would be y arrow y. Okay, that could also happen. All right. So we have this idea of a type substitution, and we think of being able to apply it sort of as like a function, right? If you think of it this way, so like what's the type of sigma? Well, it's a function from types to types. Okay, so it'll take some type and transform it into another one by applying the substitution, by replacing some of the variables with types. Okay. So this is going to be an important idea. Okay. Right. And so now here's kind of the big idea here, the big sort of paradigm shift in how the type checker will work, is that we're going to move to what we'll call constraint-based type checking. Okay. And the idea of constraint-based type checking is that, so you guys are probably working on PA6 now, or hopefully you've started. And so when you implement the type checker, it's a recursive program that just kind of traverses the expression recursively, doing the type checking. And as it goes, it's kind of making sure that things match up, right? So if you're type checking an addition expression, like a binary expression that for plus, then you'll make sure that the two sides have type num. And you're checking that as you're going along. That's the type checking. And if they do have type num, then you proceed and you say, okay, the whole expression has type num or bool, depending on, well, if it's addition, then it'll be num. Okay, and if they don't match up, then you throw an error. And so the type checker can fail. If it's checking as it goes along at every point, and as soon as something is wrong, it just fails. There's an error and says there's a type error. So with constraint-based type checking, we're going to do something a bit differently, where instead of actually checking the things right there on the spot, we're just going to record constraints that assert their equality. So if we say that if we expect two types to be equal, then we'll record a constraint that says, well, this type is equal to that one. Or if we expect a type to be num, then we'll just record a constraint that says that it's equal to num. Okay, so suppose you've got like an addition expression where who knows E1 and E2. Okay, so your normal strategy for type checking would be, well, type check E1 and type check E2, and then make sure that they're both num. And if they're not, you fail, right? And then, but if they are, then the whole thing will be num. But in constraint-based type checking, all we're going to do is just kind of record the constraints as we go along. And we'll say, okay, well, let's say that you type check E1 to get some type T, and you'll type check E2 to get some type T2, and then you'll record some constraints saying that, well, T1 should be equal to num, T2 should be equal to num. Okay, and then you could return num here, or you could like generate a new type variable for the whole thing, and then say like x should be equal to num. There's a couple ways you could go about it, but the idea is that it's because whenever you type check E1, now this could be a type variable, or it could contain type variables. Okay, and so you can't really. We're not going to try to check right here and now. We're just going to record the constraints as we go along. So the type checking algorithm, while it's essentially the same thing as before, the only difference is that now you're just recording a bunch of constraints as you go along. And so at the end, you end up with a big set of constraints, a constraint set, okay, which is like, it's just a big list of equality constraints, of equations, okay, where I ranges over like, 1 and, okay, it's just some finite set of equations. And so then the goal after that is to try to solve this constraint set, is to find a way to satisfy them all, okay? Okay, and so this part of the algorithm, though, it doesn't fail anymore. It just builds up a big list of constraints. And now your job is to try to find a solution for this constraint set. So what does that mean? Well, we'll say that a type substitution sigma is a solution for constraint, or I could say, it solves or it satisfies the constraint set C if when you apply the substitution to all the types here, then you end up with just a bunch of identities, right? So if it actually renders all the types equal, okay? So I'm not sure how we would write this. Something like if sigma Si and sigma Ti are identical for all I, okay? Where each one of these is drawn from the constraint set, okay? And so what we could also call this is solution or a unifier, okay? So sigma is a unifier for C.
When you say the constraints are recorded, where are they recorded at?
That's when we did the type checking algorithm, where it traverses the whole expression, and as it goes along, it's building up a list of constraints. And so, for example, here, actually what you get. So, say you're type checking an addition expression like this. When you type check E1, you get back not only T1 but also a list of constraints that were necessary. Like these constraints need to be satisfiable in order for E1 to be well typed. So you'll get T1 and C1. I didn't write that. And then when you type check E2, you'll get T2 and C2, some more constraints. And then what we'll do is for the whole list of constraints, it will be C1 along, with C2 plus some extra ones now. We say, well, we also expect T1 to be dumb and T2 to be dumb. So, you do this whole thing where you recursively traverse the whole expression and build up a big set of constraints. And then you say, well, if we can find a unifier for this constraint set, then the term is well typed. And the unifier is a type substitution. And so then the type of the term will be what you get from applying the unifier to the type that the algorithm returned, because it could contain a bunch of type variables and stuff. But this is the basic idea for doing type inference. Because what we're going to have is an algorithm for doing this. We're going to have an algorithm for solving constraint sets like this, for finding unifiers. And not just finding any unifiers, but finding principal unifiers, the most general ones. They're the best. There's a way we can I'll write it down to make it more precise, but there's a notion of kind of what's the best unifier to find. And so, this stuff is really neat because it's not that hard to implement. We'll see that the algorithm for solving for these is actually quite small and simple. So you can implement this yourself. And it's really kind of amazing because this is real type inference. Because sometimes when it always kind of annoys me, or I have to laugh when I look at, if you go to the Wikipedia page for some language like C# or whatever, I'm not sure, and they'll say, well, the language has type inference, but then what they mean is just that when you're declaring a local variable, you can leave out the type annotation because it can just copy over the type of the expression that you're initializing it with. But then that's it, and they say that's type inference. But that is a joke compared to what you get with this kind of type inference. This is full type inference. You can leave out all the type annotations in the program. You don't have to include any. And it will infer all the types, and not just any types, but the best. And this is the kind of type inference that you have in languages like OCaml and Haskell, probably F#, I don't know. These the languages that are built on the Hindley-Milner type system. That's what we're looking at. So, right. So it's kind of amazing how good it is. So that's why I want to cover it. It's cool. All right. So, right. The way to do this, the algorithm for finding unifiers is called unification. Okay? Whoops. And the idea of unification, it goes back pretty far. And it's actually a pretty general algorithm. It's a general idea. So it has applications not just for type inference, but it's useful for all sorts of things. And Prolog is based on unification. It's kind of at the heart of the way that Prolog does computation. It's really uses unification. Okay, so it's a really fundamental algorithm. And I remember, I never learned about unification in my undergrad. And to me that was kind of, like I learned about it later on, and then I thought it was rather disappointing that I never learned about it in undergrad. So, that's why I'm doing this here. Okay? Right, and so the idea is to kind of look for the best, where we haven't defined what that means yet. The best solution for a set of equations. All right? So what do we mean by best? Well, here's what we'll do. What do we mean by best? Well, I'll write something like this. I'll say, suppose you've got two type substitutions, sigma and sigma prime. Okay, well, I'll say that sigma is like less than or equal to sigma prime, and I'll write it with a little square thing. So we're going to define an order relation on these. I'll say that sigma is less than or equal to, or you could pronounce this as sort of like sigma is less specific or more general. Oops. Than sigma prime. If there exists another substitution, I'll call it little gamma, such that, let me make sure I get this right. All right, such that sigma prime is equal to, I think it's gamma after sigma, right? Yep. Okay. Okay, so this is composition. Composition of substitutions. If you recall, you can think of a substitution as being a function from types to types. So this composition is gamma after sigma. It says, well, this itself is a substitution that you get by just taking the input type and passing it through sigma, and then passing the result of that through gamma. Okay, so it's like do sigma first, do that substitution, and then do gamma. Okay, so we're saying that sigma is like less specific or more general than sigma prime if sigma prime can be written in this form where, well, it's just the same thing as sigma followed by some more stuff. Okay, so the idea is that that sigma prime kind of does more substitution than sigma. Okay, sigma prime is the same thing as doing sigma first and then something else. Okay, but of course this could be the identity. So this is a reflexive relation. Okay, so sigma is less than or equal to sigma for every sigma. All right, so that it's like less than or equal to, not strictly less than. Okay. So now, let's see. Now we can define what we mean by the best solution or the best unifier. Okay. I'll say that. Let's say this. Okay. So given a constraint set C and a unifier for C, sigma, say sigma is a unifier for C, then sigma is a principal unifier for C if what? Well, first it has to satisfy C, but we've already said that. If it's less than or equal to sigma prime for all sigma prime that also satisfies C. Oops. Okay. So this is what we mean by the sort of the most general unifier for the constraint set is that, well, if you, for any other unifier, this one is more general than it. Okay? That you could obtain that one by first doing this and then something else. So it kind of does the least work. You know, the most principal, or the principal unifier, the most general unifier is sort of the unifier that does the least work. And so it turns out that if we find an algorithm for finding principal unifiers for our constraint sets, then that will give us the most general types, you know. So that, like our example from before, where was it? Right here. Okay. So suppose that we were type checking this. What we would end up with is something that looks kind of like forget about this. We'd have like an x arrow x, and the question is, well, let's see. What would our constraints be? I suppose we wouldn't have any constraints. From type checking this, our constraint set would be empty. So it's sort of a trivial case, because then you'd say, well, given an empty constraint set in this type, or like, you know, what's a unifier that you know, satisfies the empty constraint set? Well, it could be anything. Okay, so maybe this isn't the best example, but obviously the empty substitution would be the most general one because it does the least work. Okay, so then you'd be left with just x arrow x, and that's why it gets left at x. But I'm kind of skipping ahead, so maybe I shouldn't do that. Okay.
So once you've identified a principal unifier, you've identified a general solution for just two types for the whole thing.
For the whole constraint set. So you'll have a set of constraints that, where was an example? So a constraint set could look, what's an example constraint set? Actually, we've got some examples here. Yeah, let's do some example constraint sets. Suppose we've got one that looks like this. There's one equation that says x equals num, and then you've got another equation that says y equals x arrow x. Okay? This is a constraint set. So then, you know, if you've got a type substitution sigma, then you can apply it. Okay, we also have this idea of applying a type substitution to the constraint set, and all that does is just goes into all the types and applies the substitution to them, right? So now we could ask the question for this constraint set, what's a principal unifier? Okay, what's the principal unifier for this constraint set? Okay, what's a sigma? What's a substitution that sort of maps variables to types that will unify this constraint set? We don't have many options, but does anyone have an idea? Well, let me erase that sigma. Say this is C. Let's see. Well, maybe I'll do square brackets. Well, from this first equation, there's only one way that we can make this satisfied, which is by setting x to num. Okay, we're forced to make x num here. Okay, so we have to do that. We're going to have to map x to num. Okay, And then if we're mapping x to num, then this whole thing becomes num arrow num. So again, we're forced now to map y to num arrow num. Okay, and so that, I mean, that's probably the only unifier for this constraint set. So it's sort of trivially the most general one, because, well, it's not very general at all. It's actually very specific. Okay, and so then if you apply this unifier to C, then you see num arrow num and num equals num. Sorry, num arrow num equals num arrow num, right? And so you can see all the equations have been turned into these identities. They're just identical sides. So that's why this sigma is a solution for C, because when you apply it to C, you get a bunch of trivial identities. Okay. So now I guess what we can do for the rest of the time is look at the unification algorithm. Okay. So the idea is that you're given a constraint set. That's the input to the algorithm, and the output should be the principal unifier for the constraint set if it exists. Or actually, I mean, maybe we should just look at more examples of constraint sets. That might be helpful. Let's do that. Let me see. Here's another constraint set. I'll say C equals num arrow num equals x arrow y. Okay? So now we want to find a unifier for that. We want to find a type substitution that solves the constraint set. Anyone have an idea? Yeah?
Would it be x equals num, y equals num?
Yeah. So let's map x to num and y to num. Whoops. Yeah, so again, our hand is forced here. There's not much of a choice. That's the only way to make this, it's the only way to satisfy this equation. Okay, let's try another one. Let's let C be, it's kind of interesting. So x arrow y equals y arrow z, and z equals u arrow w. Now what can we do? What can we do? Any ideas? Make sure that I've got it right. Interesting. I see. I suppose there's more than one way to write this, but okay. So, well, our hand is forced in a certain way here for this first equation. Say, well, for x arrow y to be equal to y arrow z, well, then we'll need x to be equal to y and y to be equal to z. Right? So, we don't have to choose num or anything. I mean, obviously, you could unify this by just mapping them all to num. that's more specific than is necessary. We want the most general thing possible, so let's just do the least amount of work that we can. So, well, we need x and y to be the same, and we need y and z to be the same. Okay? So actually, they all need to be equal. And then we know from this one that, well, z needs to be equal to u arrow w. And, well, we have already established that z needs to be equal to both x and y. So what we'll do here is just map all of them to u arrow w. So y is the same thing. Z. Okay. So that will be it. Now, what happens when we apply the substitution to the constraint set? What does that first one become? It becomes kind of big and weird. So u arrow w, arrow u arrow w, okay, equals the same thing. And then, again, u arrow w equals u arrow w. Just, right, they all become u arrow w, okay? But it does satisfy the constraint set in the most general way possible. Okay. So now, if you had some other substitution, like say sigma prime, that could be more specific than this. It could say, well, let x be num arrow num. Okay, and let y be num arrow num, and let z be num arrow num. Okay, well then, this substitution is not the principal substitution, because it can be factored into two parts, where the most general substitution it comes first. So then sigma prime could be equal to what would it be? This one, a substitution that sends u and w both to num. Oops. After sigma, okay? So the idea is that, well, first map x, y, and z all to u arrow w, and then take u and w and map them to num, okay? And that will give you sigma prime here, which maps x, y, and z to num arrow num. Okay. So the idea is that this one, or this sigma here, is the most general unifier, the most general solution to the constraint set, because any other unifier can be kind of factored in this way, where it's the most general one followed by some more stuff. Okay. Okay, let's look at one more example. About out of time, so we're going to have to push back the unification algorithm for Monday, and then we can actually implement it, I guess. So maybe whatever. Sorry if you were looking forward to it. Let's look at one more example here. Let's say our constraint set is num should be equal to num arrow y. Okay. Now what's our principal unifier? The only variable is y, so.
None equals y.
Okay, let's try it. So let's say we map y to num. Okay, and now let's apply this unifier to the constraint set. You'll get num equals num arrow num. That's not quite right. These two sides are not identical. So this doesn't work. This is not a unifier for the constraint set. It doesn't solve the equation. Any other ideas? Yeah?
Would it be some sort of like movie type?
Say it again?
Like empty type, like
Oh, empty?
yeah, something
Well, I mean, you're kind of right about that because there is no solution. Yeah, there is no sigma here that will unify this constraint set. Okay, so this could come up in our context because remember our constraints are generated by the type checker. So something like this can happen when the expression we're trying to type check isn't well typed. You know, when some types are not matching up correctly. When you have a type mismatch, then this is where you'll find it. Whenever you've got the constraints and you're trying to find a unifier, and you'll find that nothing you do works, right? And that's where the type errors will come from for us. And they'll come up here, but you know we haven't gotten to that yet. So that's what we'll look at next time is the unification algorithm. It's surprisingly simple. Okay, so it's kind of a beautiful thing. But that'll have to wait. Okay, so let's see if we have a quiz. And then we have the help session tonight, and PA6 is due tomorrow. I should also mention that PA7 is already posted if you want to get started. At least one. I don't know if I'm going to have another option available for it, but there's one that you can do. Okay, and so you can take a look at that. I might give some kind of open-ended options where, you know, I don't provide you with a template really, but I just say, well, you know, take PA6 and you know, make it polymorphic or something like that. Okay, but I don't know yet. All right, so let's see if we have a quiz. Oops. Okay, let's see. All right. See you Monday.